All right, here's how the mean value theorem works. Imagine that we have an interval, and that interval starts at A, and that interval ends at B, and you have a point right here, and you have a point right here, which means that this is f of A, and boom, this is f of B. Now I'm going to ask you to draw a curve that connects these 2 points, and there's 2 requirements. It needs to be continuous, and it needs to be differentiable. Doesn't matter how you draw it. You can draw it any way you want, but it has to meet those 2 conditions. So here I go. Bum, 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 bum. All right. Now something interesting about my curve and any other curve that we could have drawn. Imagine the line that connects the endpoints. This line describes the average rate at which this function changes, because it is equal to the change in y on the interval divided by the change in x on the interval. Now what I notice is there's a point on my curve right about there. And at that point, imagine that I were to draw the tangent line. I can't help but notice that my tangent line, which describes the instantaneous rate of change at this moment, has the exact same slope as the average rate of change line. Well, here's what the mean value theorem says. It says that if you've got a curve, and that curve f is continuous on an interval, and that curve is differentiable on the same interval, differentiability, we don't worry about the endpoints, then here's what's guaranteed. There is some point between A and B. We'll call that point C. So then there exists x equals C such that C is between the start and the end of the interval. And here's the big reveal. The instantaneous rate of change at C is equal to the average rate of change on the interval. So in other words, the instantaneous rate of change at C is equal to the average rate of change on the interval. Okay, that's the mean value theorem. Now let's quickly talk about why it has to be continuous and differentiable. I'm going to make another interval. So here's A, here's B, and here's f of A, and here's f of B. And here's the line, boom, 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 that gives us the average rate of change. Now imagine I relax the condition about continuity. Then we could do this. Notice that now there is no point between A and B where the slope or the instantaneous rate of change is equal to that average rate of change. So continuity is required. Second, let's talk about differentiability. Same game. Here's f of A, here's f of B. Here is the average rate of change on the interval. If we relax the differentiability requirement, then we could do something like this. Notice that we've got that cusp there. So now slope is too big, slope is too small. There's no point where the slope is equal to the slope of this line. Go to the next video for some examples. So here's an example of a mean value theorem problem. We have f of x is a quadratic function on an interval from 1 to 4, and we want to know what value, what x value meets the conclusions of the mean value theorem. So it's a 3-step problem. And the first step is going to be to find the average rate of change. So I'm going to plug 1 into the function, and I get 2. And then I'm going to plug 4 into the function, and I get 16 plus 4 is 20. And I know that this function is concave up everywhere, so the graph is going to look something like that. And the average rate of change would be equal to 20 minus 2 divided by 4 minus 1, which comes out to be 6. Next thing is I'm going to kind of estimate the point where the instantaneous rate of change is the slope, is the same as the average rate of change. So step number 1 was finding that average rate of change. Step number 2 is calculating an equation for the instantaneous rate of change, which is like saying, what is the derivative? Well, our derivative, or our rate function in this case, would be 2x plus 1. So that brings us to the third and final step, which is that we need to set the average rate of change equal to the instantaneous rate of change. As I'm looking at this, it looks like it's going to be somewhere 3 or maybe a little less than 3 based on my picture. We'll see. So the average rate of change was 6, and the instantaneous rate of change is always 2 times x plus 1. And if we solve that equation, we get that x is equal to 2.5, which seems pretty reasonable for my drawing, that this would be at about 2.5. I'm going to do one more example with you. Example number 2, here's g of x. It is x minus 3 to the 2/3 power. And here's the interval that we're given, -5 to 11. And once again, we want to figure out what value of x will make the instantaneous rate of change equal to the average rate of change. Now, I know that you're not usually going to do these problems using a graph, so let's try to do this one without. So remember what the first step is. It's to find the average rate of change. And how would we do that? Well, we would take this and plug them in here. So that's g of 11 minus g of -5, all divided by 11 minus -5. So on top, if we plug 11 in here, 11 minus 3 is 8. 8 to the 2/3 power would be 2 squared, which is 4, minus, plug a -5 in, that's a -8. The cube root of -8 is -2. Squared is 4, and the denominator is 16, but that doesn't matter because the numerator is 0, so that means that our average rate of change is 0 on this interval. So second step, since we want to find where the instantaneous rate of change is equal to this, we'll say, when is IROC equal to, let's see, g prime of x is 2/3, using the power rule here, of x minus 3 taken to the -1/3 power, which I could rewrite as 2 divided by 3 x minus 3 to the 1/3 power. Step 3, take the AROC, set it equal to the IROC, so we get the average rate of change is equal to this. And what you'll notice is that this has no solution. So we ask ourselves, why is that? And the answer is that we violated one of the conditions. Here's what the graph looks like. See that it is not differentiable at 3, which means that the conclusions of the mean value theorem might not be true.